Hi, this is the second movie that I've made containing a review of thermodynamics. I'm Jos Thijssen and I teach the course on statistical mechanics at the Master Applied Physics at the Technical University of Delft. There is also a first movie and I just continue now where the first movie stops. So at the end of the last movie we have seen that there are different potentials that you can define and they are related through Legendre transformations. Now the first potential that we have analyzed was the free energy, the Helmholtz free energy. And if you look at a small change of this energy with one of its parameters, t, v or n, then this is the expression that gives me the change. So, for example, if we take df dt we get minus s, if we take df dv we get minus p. But now suppose that we take a double derivative of f with respect to t and to v, then if f is a well-behaving function, we can interchange the order at which we take those derivatives. So that leads to so-called Maxwell relations. So we just saw df dv is minus p, df dt is minus s. And so I can take the second derivative of f with respect to dv and dt. And if I take first the derivative to v, with respect to v I have p, and then I take the derivative with respect to t, so I get minus dp dt. If I do it the other way around, so I first take df dt, gives me minus s, and then take the derivative of s with respect to v, these two, if f is a well-behaving function, should be equal. And so this is a Maxwell relation, and I can do this for these two, but I could also do that for a relation involving the chemical potential, or I could start not from f but from one of the other potentials like the Gibbs potential or the Grant potential or the enthalpy, and each of those will give me a different series of so-called Maxwell relations. I've now illustrated how you derive them for one particular case, and usually it's advisable to know how you derive them because it's almost impossible to remember them all with the right signs. Okay, then we continue with the Euler relation. And for the Euler relation it's important to go back to the basics of thermodynamics, where we have seen that their entropy is an extensive variable, and it's itself also a function of all the extensive variables. So in the case of a monatomic gas, which is the standard example, we see that S is a function of E, V and N, and E and V and N, they are all extensive variables. So what that says is that if we would scale up the system by a scale factor lambda, or scale down if lambda is smaller than 1, then we see that f's of the larger system, so we have now lambda E, lambda V, lambda N, should be lambda times the S of the original system. That's quite an obvious result, but it leads to a very interesting conclusion, because we can take now the derivative of this equality with respect to lambda on both the left and the right hand side, and then we can put lambda equal to 0. Now taking the derivative, for example, with respect to this lambda, means that we take the derivative of s with respect to its first argument, which is the energy argument, and then we have to take the derivative of this with respect to lambda, so that gives me an e. So I get e times the SdE. I set lambda equal to 0, so it's really e times the SdE. For this term we get the same v times the SdV, and then for the last term n times the SdN. Well, on the right hand side there is only a lambda in front of the s, so that drops out when taking derivatives, and I have this relation. And now I realize that we know that dsdE is 1 over t. Furthermore, the SdV is P over T, and the SdN is minus mu over T. So I get this relation, which after multiplication by T and moving E to the left hand side gives me this expression. E is minus Ts minus PV plus mu n. An important relation in thermodynamics, and it's called the Euler equation. And it has also an interesting consequence, because we know that if we take dE, then we get from the first term T times ds plus S times dt. Second term gives me minus P dV minus V dP. And the last term gives me mu dN and n d mu. Now we know from the first law that dE is the heat, TdS, minus the work. And we have two types of work. First we have the mechanical work, and then we have the work involved in changing the particle number. That's mu dN. And so we see that three of those terms we know that they are equal to dE. So we can say that the rest of those terms, the remaining terms, SdT minus VdP plus n d mu, they should all add up to 0. And that's the famous Gibbs-Duhem equation. SdT minus VdP plus n d mu equals 0. So that's one important consequence of the Euler relation. There is another interesting consequence, and that pertains to the Gibbs potential G, which was defined as E minus ds plus PV. Remember that we had first performed a Legendre transformation in order to remove the S, and that was the term minus ds. It's replaced then by T as a parameter. And then we did an additional Legendre transformation which removed the V dependence and replaced it by a P dependence, and that gave the second correction to E, or the second term in addition to E. And so using the Euler relation, we can replace E by Ts minus PV plus mu n. So the first three terms here are equal to E due to the Euler relation. And then we had these other two terms, minus Ts plus PV, and so they cancel against these two, and we are left with mu n. So we see that the Gibbs free energy G can be written as mu times n. It's n times the chemical potential. Well, most of the analysis so far was specific for a gas consisting of one type of molecules, a unimolecular gas. But in general, we can also look at gases consisting of more particles, and we can look at completely different systems, not gases but magnets, for example. And always, so in general, we can write the entropy as a function first of all of the energy. So the energy is always an argument of the entropy, and the other extensive variables, they can be the number of particles of species 1 or species 2, and we will shortly see how that looks like in the case of a magnetic system, which is completely different. Now, because we know that ds/dE for all the x's constant is 1 over T, and because the temperature is always positive, this one is always positive. Temperature 0, then it would go to infinity. So I can always invert S as a function of E, and I get E as a function of S plus the other dependencies. And from this I can define the concept of generalized force. So in the case that X is the volume, then the F would be the pressure. If X is the number of particles, then F would be the chemical potential. So F is just the derivative of E with respect to Xi, and therefore if we look at a small change of the energy due to the fact that the system does any work, we can immediately infer from this equation, using a Taylor expansion, that this would be minus the sum over I fi dxi. So if I vary the parameters xi a little bit, then I have a change in E, and that is then the dw. Of course, I do change all the x's, I do not change the s itself, because if I would change s, then that would represent a term which means the heat. So here again, the example is if xi is v, then we have fi is minus p, and I get dw is p dv. So that's associated with a volume change. If I change the number of particles, I can derive a work associated with that change in n, and I get a mu dn. And obviously, in general, I have to add all these forces. So let us then proceed looking at a completely different type of system, a magnet. And a magnet, in that case, I also have n, that's the number of magnetic moments. But these magnetic moments, they will orient themselves, and if they are oriented in majority into one direction, then we have a so-called magnetization. So the more magnetic moments are oriented towards one direction, the bigger this magnetization. In general, that can be a vector quantity, but that depends strongly on the system. So let us assume that it's a scalar here, so we look at the magnetization along one axis, along the axis along which we apply an external field like H, and then it turns out that the change in energy with respect to this m, and m is the extrinsic variable. If I take two magnets, I have twice the magnetization, but the field H is the intrinsic variable, because if I put two magnets next to each other, that doesn't change the applied field. So looking at the work according to our definition would be minus mu 0 h, that's the generalized force, minus the force times the change in the external variable, so that's the m, extrinsic variable, sorry. So the total change in energy is then the heat added to the magnet, plus mu 0 h dm plus mu dn. But this would mean that the m is a variable that I can control. Now in experiments that is very rarely the case, I guess it's never the case. We always apply the external field, so that is under our control, and then we have to wait and see what the magnetization is. So I would like to change this magnetization, I would like to replace that by the field, and we know how to do that. Then we perform a Legendre transformation with respect to m, and following the rules of Legendre we get a new quantity. In fact, if this is really the energy as a function of S, m and n, then this would be a kind of enthalpy, and I get E minus mu 0 h m. But of course we also usually control the external temperature and not the entropy of the system. So we should also perform a Legendre transformation with respect to S. And again, we follow the rules, we subtract a factor of Ts, and then we have a thermodynamic potential, which we can best describe as a Gibbs free energy, because we have performed two Legendre transformations analogous to what we would do in a gas, and so this G is a function of the parameters that we usually have under control. That is the temperature, that's the external field, and that's the number of particles. In everyday life we very often heat up systems, like when you boil water for your tea, or when you heat the water in the washing machine. And the relevant question is, of course, how much energy that costs. So how much heat do I have to put into a system to change its temperature by a certain amount? And if the temperature increase is small, then we expect that the heat dq is proportional to dt, and this proportionality constant is called the specific heat. Now the specific heat can be calculated for a system for which you keep the volume constant, then it's called CV, or the system for which you keep the pressure constant, that's CP. Now if you keep the volume constant, let's try to write the CV in a different way. So CV is dq dt or TdS dt. We keep the number of particles and the volume constant, and because the volume is constant, the system cannot do any work, and so the only way in which we can change the energy is by putting heat into the system. And so the TdS is in fact in this case the same as the E, and therefore we can write the CV as dE dt at constant N and V. Now could we do the same for CP? In other words, could we also write CP is dE dt and then change the V here by a P? Well, that turns out not to be the case. In fact, if we analyze this, we start by writing the V as a function of T, P and N. Well, N is kept fixed, so that's not so important, but we usually have for a gas, we always look at the so-called equation of state. Like for the ideal gas, that's P times V is NKT. So that is the equation of state that we will use, and suppose that we have an expression for S as a function of T, V and N. Well, in that case we can write CP, so that's TdS dt at constant P. Now we need to take the derivative with respect to T, so there's one derivative here, so that gives me TdS dt, constant V, and there is also a derivative here from the V, because that also depends on T, and we need to keep the P constant. So in the derivative of S we need to consider T as a constant parameter. We take the derivative with respect to V, and then we use the chain rule. We get dV dt at constant P. Now the ds dV is a quantity that we would like to rewrite, and we can do that. We can replace it by dP dt. That is a Maxwell relation, which tells me that ds dV at constant T is the same as dP dt at constant V. It's in fact the Maxwell relation that I derived a few sheets above. So here you can see it. dP dt is ds dV, and I've just used that here. In order to analyze the second term, the dV dt at constant P, we look at a general rule that is quite important in thermodynamics. So suppose we have a function f which depends on two variables. Then if we look at a change in f, df, it can obviously be written as df dx at constant y times dx plus df dy at constant x times dy. Now if we want to know what dx dy is at constant f means that this df should be 0. And then from the fact that this is 0, we immediately can infer that dx by dy is the derivative of f with respect to y constant x divided by the derivative of f with respect to x constant y. So this is just the quotient of these two, and there is a minus sign because I had to bring one of those terms to the right. Now we can put this one upside down and move it to the numerator, and we get this. And so let us now apply that to dV dt at constant P. So P plays the role of f, V plays the role of x, and T plays the role of y. And then using this rule we see immediately that this can be written as minus dP dt at constant V times dV dP at constant T. Now we had already a factor of dP dt at constant V here, and remember please, we are now looking at the second term. We are rewriting this term. So this term generates one extra term, dp dt and the minus sign, and then there is a dv dp. So we can write now this first term. TdS dt was evaluated at constant V, so that's my CV, specific heat at constant volume. And we get this minus sign, two terms with dp dt, so that's dp dt at constant V squared. And then we have this term, dv dp. And I can also write that in the form CV plus TV alpha squared kappa. And here we have some important quantities, like we have kappa, which is minus 1 over V dV dP. That's the compressibility. It tells you that if you increase the pressure, then how much is the increase of the volume of in the volume of the system. And then there is this quantity alpha, which is the expansion coefficient. So alpha is 1 over V dV dt. It tells you how much the system will expand when you increase the temperature at constant pressure. So that's just the expansion coefficient. And so using these definitions, it's easy to see that this complicated term here reduces to TV alpha squared over kappa. Now the details are here not that important. What is really important is that you realize that Cp, that's this term here, so Cp is not equal to Cv. There is an extra contribution, and that contribution depends on the expansion coefficient and on the compressibility. Finally, it's useful to note that for ideal gases we usually define the quotient of Cp and Cv as gamma. So I just mentioned this because it often occurs in problems. So now we would like to study the thermodynamics of chemical equilibrium. So if you have a chemical reaction, you have a series of species. Those are here the A1, A2, etc. up to AR. And they react and produce different species, AR plus 1 up to AK, and the reaction can go both ways. And then we have these important prefactors which tell you how many molecules of each species you need in order to produce a particular amount of molecules on the right hand side. And as an example, you can think of the common recombination of hydrogen gas and oxygen gas to produce water, and that also goes the other way around. And what we would like to do is study the thermodynamics of such a system, say a vessel with oxygen, hydrogen and water, which is in equilibrium. Now if we increase H2 and we increase the O2, then it means that the H2O needs to decrease. Also the other way around, if we decrease these two, we use them to burn the H2, and we produce this one, so this one is an increase. So increase on the left is decrease on the right, decrease on the left is increase on the right, and therefore it's useful to change these numbers a little bit. We make them negative if they are on the right hand side. So nu r plus 1 up to nu n, they are negative. And looking at this example, you can convince yourself that a change in the concentration here divided by the appropriate prefactor is the same for each species. So for example, I need to burn 2 hydrogen molecules. So I divide that then by 2, and then I get the same number as I have oxygen molecules. And with the new case having a negative sign on the right, this is an equation that holds for all these species on the left and on the right hand side. Now suppose that we perform this reaction in a vessel where the pressure and the temperature are constant. Then the chemical potential, the thermodynamic potential that we should look at is the Gibbs free energy. That should acquire its minimum. Well, we have seen before, and that was a consequence of Euler relation, that the Gibbs free energy of a particular species is the chemical potential times the number of particles. So if I have different species, I just add up all these Gibbs potentials and then I get the total Gibbs potential. Now we use the requirement that G is minimal, so the dG should be 0. And the only thing we can change is the concentrations. So we have a sum over mu I, d and I. And these d and i's, they are proportional to the nu i's. So we get mu I times nu I. And that should be 0. So the conclusion is that in chemical equilibrium this should hold. The sum over mu I times nu I is 0. A strongly related problem is that of phase coexistence. So in the case of chemical equilibrium we have different chemical species that are in equilibrium with each other. In the case of a phase transition that takes place and we are at equilibrium, we have often two phases that are in equilibrium, like gas and liquid. So we take gas and liquid here as a particular example, and if they are in equilibrium, we know that their chemical potential should be equal. So we could also say that a new gas is in fact minus the new liquid, and then we immediately see that this should hold in view of this relation. Okay. Now the sum of the number of gas and liquid molecules, that's the total number of particles in the system, and I keep that constant, so that a change in the number of gas particles is equal to minus this change in the number of liquid particles. If I have a growth of gas molecules, then I have the same decline of the number of liquid particles. And so we immediately see, in that case, if they have the same chemical potential, that the change in G is always 0. So it doesn't matter how many gas and how many liquid particles I have, the Gibbs free energy is always independent of the relative numbers. And that is why in coexistence there's never really a drive to go from one phase to the other. I mean, any mixture of these phases is stable. And so the difference with chemical equilibrium is that there is usually a very strong difference in the volume that the liquid and the gas particles occupy. So with a liquid is dense, so each particle occupies a small volume, and we define VL, small VL, not the capital V, as the volume per liquid particle. And in the gas phase, that volume is a lot smaller, we call that Vg, so that's the volume per gas particle. And the total volume, that's the capital V, that's the number of liquid particles times the volume per particle plus the number of gas particles times volume per gas particle. Then we can also define the little v, which is the average volume per particle, V over N. And if we fix the temperature and we follow now a curve in the VPV plane, then there is a region where the G is completely insensitive to the relative contribution of NL and Ng to N. And so if everything is liquid, then the particles occupy a very small volume, so then we are here. And if everything is gas, then we are here. So this is a region, it's called the coexistence region, where the volume, the average volume per particle, can vary a lot, and it means that liquid and gas particles are coexisting in arbitrary proportions. So if we have a particular temperature, then once we hit with the pressure precisely this value, then I have the phase transition and then I have coexistence. Related to this problem is the Clausius-Clapeyron equation. So now I have drawn a different graph, which is the graph of P versus T, so pressure versus temperature. And in this graph there is a certain line which characterizes the situation where the chemical potential of the liquid phase is equal to the chemical potential of the gas phase. And so if that is the case, we have a phase transition and there is coexistence. And this defines a line in the PT plane, and that's the phase transition line. It's this black line here. And left of this black line we have a liquid, right of the line we have gas. And the question I would like to address is, suppose we are at this point, the red point, and so there the mu liquid is equal to the mu gas, and we want to move along the line. So we move towards the green point where I have changed the T by an amount delta T, and I've changed the pressure by an amount delta P. So suppose we are still at the line, so the mu liquid should be still equal to the mu gas. Can we find a relation for this point, this green point, with respect to the red point? Well, in fact, what we can find is a relation for the derivative of P with respect to T. And we do that obviously by performing a Taylor expansion. So the change in mu liquid, when I go from here to there, that's called delta mu liquid. So that's the difference of the new mu liquid minus the old mu liquid, and similarly for the gas. They should be the same. So we perform the Taylor expansion as announced, and what we obtain is d mu liquid dP at constant T delta P plus d mu liquid dt times delta T at constant P, and we do the same for the gas. Okay, so we do the same for the left hand side as we do for the right hand side. Now we divide left and right hand side by delta T, so that we get delta P divided by delta T. If we take the delta small, then we have a derivative there, dP dt. So here we have a dP liquid dt, and here we have a dP gas dt, and here when we divide by delta T we just get ones. Now we would like to know obviously what the d mu liquid dP is, what the d mu liquid dt is, and in order to find an answer to that, we realize that the Gibbs free energy is directly related to mu. It's mu times n, as we have seen several times before. And if I work out via the first law the small change in G as a function of the parameters T, P and N, so this should be a dN, I find this equation, and so we immediately see that d mu liquid dP, so that's this term, gives me V. I'm looking at mu, so I have to divide by N, so I get the liquid volume per particle. If I look at d mu liquid dt, I get this minus S divided by N gives me minus small s liquid, and small s liquid means the entropy of the liquid per particle. So it's the total entropy divided by the number of particles. I do the same for the gas, and then immediately I find the following relation. V liquid minus V gas times dP dt is minus S gas plus S liquid. And so I can then transform this equation into dP dt. That's the slope of this phase transition line. So that's the slope of the black line in this diagram at any point is given by the difference in entropy, and I have to divide that by V gas minus V liquid. Now, because the entropy because we keep, suppose we are at one particular temperature, then we can write this as a heat divided by T. So the difference in entropy between gas and liquid is delta Q over T, and if I calculate that per particle, then that is the so-called latent heat. What does that mean, the latent heat? So the latent heat is the amount of energy I have to put into a substance in order to bring it from one phase to the other. And now, talking statistical physics, this would mean that in order to go from a liquid to the gas, I have to break all the bonds between the liquid molecules. And those are usually van der Waals bonds. I have to break them all, and so I have to put heat into it. That's this latent heat. And so if I compare that with the change in volume, then that tells me the slope of the phase transition line in the PT diagram, and this is known as the Clausius-Clapeyron equation. And so that completes this review of thermodynamics. I hope it was useful. Please inform me about any comments or opinions that you have on this movie or the previous one. Thank you.